This video is about Rolle's theorem. Let f be continuous on the closed interval from a to b, and differentiable on the open interval from a to b. If f at a equals f at b, then there is at least one number c in the interval ab such that f prime at c is equal to 0. Well, you know how they say a picture is worth 1,000 words? Let me sum up this whole theorem with one simple picture. So the key is f at a equals f at b. So here is f at a, and here is f at b. Notice they are at the same level. That's how we know they are equal. So if we have a continuous function, if I start here at a, whatever else I do, eventually I'm going to have to end up at b. Now to keep it simple, I'm just going to make a more simple graph for right now. So let's just say I sort of go up and come down. Somewhere between a and b, there is going to be a point c where the derivative is equal to 0. Okay, so remember, the derivative is the slope of the curve at this particular point. So we're saying somewhere between a and b, there's going to be a point where the slope of the tangent line is 0. All right, and we'll call that c. Now, what about this part about being differentiable? So that's just to eliminate the following problem. I can start at a and end up at b and have a continuous function, but still have no slope of 0 if I do, for example, a sharp turn like this. This is still a continuous function between a and b, but there's no derivative. There's no slope of 0 in between here. All right? A function that has a sharp turn like this is not differentiable. Now, there will still be a value c that's going to be a critical number, and this point right here is still going to be a maximum, or depending on how I draw it, it could be a minimum, but just the slope of the function is not 0. There's no point where the derivative is going to equal 0. So Rolle's theorem just eliminates this as a possibility, and it only works for this. Let's see how Rolle's theorem applies to example 1. Let f of x equal x to the 4th power minus 2x squared. Find all values of c in the interval, the open interval from -2 to 2, such that f prime at c is equal to 0. So to apply Rolle's theorem, we need to know that f at a is equal to f at b. So let's take a look at that. What is the value of the function at -2? So we have -2 to the 4th power minus 2 times -2 squared. So f at -2 will equal, that will be positive 16 minus 2 times positive 4. And then f at -2 is going to equal, well, this is just 16 minus 8, so that's going to be 8. All right, so f at a, if you will, I'm thinking of the first endpoint as a and the second one as b. Now let's take a look at f at b. F at 2 is equal to 2 to the 4th power minus 2 times 2 squared. So f at 2 will equal 16 minus 2 times 4, which of course, again, is going to equal 8. So notice that these two are the same. Note. All right, f at negative 2 equals f at 2. So this fits Rolle's theorem perfectly because we have f at a equals f at b. And we also know that because this is a polynomial function, polynomials are always continuous and differentiable over their entire domain. So that also fits Rolle's theorem. So that guarantees that there is at least one value between negative 2 and 2 where the derivative will equal 0. So if we want to find this c value that makes the derivative equal to 0, we need to find the derivative and set it equal to 0. So let's go ahead and do the derivative of x to the 4th power minus 2x squared. All right, so f prime of x will equal, power rule, that 4 is going to go in the front and reduce by 1. So we're going to have 4x to the 3rd power. And again, using the power, whoops, I went too far. 2 times 2 is 4. So the derivative of the second term is going to be minus 4x. So this is f prime. Time to set the derivative equal to 0. So if we do that, we have 4x to the 3rd power minus 4x is equal to 0. There's no reason why we can't divide both sides of the equation by 4. So that will give us x to the 3rd power minus x is equal to 0. Now we want to factor out the GCF, which is x. So we will have x and then x squared minus 1 equals 0. Using the zero product property, we'll set each one of these factors equal to 0. And right away we get x equals 0. So that's one solution. If I set x squared minus 1 equal to 0, this is the difference of two squares. So I can factor this as x plus 1 times x minus 1, which is going to give me x is equal to negative 1 and x is equal to positive 1. So we have to be careful. Don't forget we're dealing with the interval from negative 2 to positive 2, the open interval. All three of these values are within that interval. So that means we have found 3 valid values of c. All right, so c can equal negative 1 or 0 or positive 1. All right, any of those will cause the derivative to equal 0. Let's just take a very brief look at this graphically. Rolle's theorem said that if the function had the same value at the beginning and the end of its interval, then there should be at least one point within the interval where the slope or the value of the derivative should equal 0. And we found 3 points like that, negative 1, 0, and 1. So here we are at negative 1, and you can see indeed the slope is 0, the derivative is 0. And here we are at 0, same story. Okay, slope of 0. And here it is at 1, where again the slope is 0. In example 1, you were given the interval for Rolle's theorem, but very often you will have to find the interval yourself. So for example 2, let f of x equal x squared minus 3x plus 2. Find the x-intercepts and then find a value of x between the x-intercepts such that f prime of x is equal to 0. So of course when you're finding the x-intercepts, that means that the value of the function is equal to 0. So we can find the x-intercepts by setting the function equal to 0. This is factorable. So this is going to be x times x, and then 2 times 1, If both of these were negative, it'll give us the -3. So factored form, zero product property tells us x minus 2 equals 0 and x minus 1 equals 0. So we get x equals 2 and we get x equals 1. These are the x-intercepts. All right, because they are the x-intercepts, by definition, that means that f at 1 and f at 2 are both equal to 0. So this fits Rolle's theorem on the open interval from 1 to 2. If we keep in mind that a polynomial function is always going to be continuous and differentiable. So that means, according to Rolle's theorem, there must be a value of x somewhere between 1 and 2 such that the derivative will equal 0. So now it's time to go ahead and find that value. We're going to have to find the derivative and set it equal to 0 and then solve it. So that should be pretty easy. So f prime of x is the derivative. This will be 2x. The derivative of -3x is just -3. The derivative of a constant is 0, so that's gone. So here is the derivative. We want to know where is it equal to 0. So we simply set it equal to 0. So that means we're going to have 2x is equal to 3 and x is equal to 3 over 2. All right, let's take a quick look at this graphically. Remember, we came up with x-intercepts of 2 and 1. So looking at the graph, you see our x-intercepts here at 2 and 1. We were looking for the place where the derivative would equal 0. In other words, the slope should equal 0. We decided that would be at an x value of 3 over 2, which is the same thing as 1.5. So here you see at an x value of 1.5, this is a horizontal tangent line where the derivative and slope would be 0.